Hello.
Hello.
Yes. Hello, Dr. Adithan. So I
Hi, how
believe
are you?
it's good morning. Yeah. All right. Okay. So yes. So we'll start the session now. So before we start, I would like to thank Ms. Wendy Pereira for organizing this webinar. Unfortunately, she won't be able to join us today. But anyways, let's proceed with today's webinar on the topic black holes and neutron stars. So we have Dr. Adithan Kathirgamaraju, the Director Research Fellow, Los Alamos National Laboratory. So he will be delivering the webinar on the topic black holes and neutron stars. So once the webinar is over, the students can ask questions during the brief time that we have. So I request all students to keep their mics muted so that it would be easy for Dr. Adithan to go on with his webinar. So Dr. Adithan, over to you.
Yeah, thanks for the introduction and good evening to you all, I presume. Good evening. I see some of you have a background of some black. Good evening. I see some of you already have backgrounds of some black holes, so it's good to know the interest everyone has. So everyone can see my screen. And let me see here. Yeah, so that's good. So everyone can see, right? I just didn't have the time to test. So Ibrahim?
Yes, it's visible, Dr. Adithan.
Okay, thanks. So I'll be talking about black holes and neutron stars. So these are some of the most extreme objects in our universe. So it's always interesting to talk about them to people who both know a lot and people who don't do much research in it, because it's very interesting. So the pictures I show you on this slide, they are really not real pictures of a black hole or neutron star. They're just images that have been generated by computers of what we think a black hole would look like. And on the bottom right is just an artist's image of a neutron star. But I'll show you what's pretty cool is we have now actual images of black holes and neutron stars that have been taken. So throughout later in this talk, I'll show you actually what they would actually look like if we look at them with our eyes. So before I get started, I need to first introduce a bit of what sort of masses or the weights we are really working with here, because they're so large, these objects in the universe. So it's very hard to get your head wrapped around these numbers. So I'll compare first the mass of the Earth. So the Earth is about 6 times 10 to the 24 kilograms. So that means I have a 6 and 24 zeros next to it, and it weighs that much kilograms, right? It's pretty heavy. You can't really imagine that sort of weight. In our daily lives, we deal with maybe 1 to 10 kilograms that we can lift, but this is like 6 with 24 zeros next to it, pretty heavy. But then if you take, around 330,000 Earths, you get the mass of a sun. So that's how much the sun's mass is. It's 2 times 10 to the 30. So that's 2 with 30 zeros written next to it. It's extremely large. So this is the mass that I will use as a reference. So when I talk about black holes and neutron stars, I'll talk about it in terms of how much they weigh in solar masses. So one solar mass is 333,000 Earth masses. So it's pretty large, these numbers we're dealing with. All right. So whenever I say 1 solar mass, just remember it's 2 with 30 zeros next to it, kilograms. Okay, so now that we have that sort of unit mass or weight unit that we have out of the way, I will talk about black holes first. So before going into what a black hole is, and do we have any chat? Yeah. Before going into what a black hole is, I will first talk about how we can make a black hole. So, if you and I were strong enough, we'd be able to make a black hole. All you have to do is take some object and squeeze it into a small enough space. So what I do when doing that is increase its density, right? So density tells me how much mass is in a certain space. So when I squeeze a certain mass in a small enough space, I'm increasing its density. And if I do that, enough, squeeze it into a small enough space, any object will become a black hole. So for example, let's take the sun. So the sun is, let's say, a ball of radius 700,000 kilometers. So that's how big the sun is. And if I squeeze the sun into a small enough ball, so I take the sun and let's say I squeeze it into 3-kilometer ball, it will become a black hole. So what makes this a black hole? Well, we have squeezed it small enough such that when anything goes beyond this, below this 3-kilometer radius, it can't escape, not even light. So this is what's called this event horizon of a black hole. For example, here, a black hole of 1 solar mass. So remember, I'm squeezing 1 sun into 3 kilometers. So this will be 1 solar mass. 1 solar mass black hole is about 3 kilometers in radius. Anything that falls below this 3-kilometer radius, the gravitational pull is so strong that not even light can escape. So this is called the event horizon. So that's essentially what a black hole is. It's this mass that have been squeezed into small enough spaces where this event or at or below this event horizon, so that anything below this cannot escape. So that's how we can make a black hole. But it takes a lot of energy to squeeze it into this mass. So you and I are not strong enough to make a black hole, although it would be nice if we could. So can we turn the Earth into a black hole? Well, the answer is yes. Like I said, you just have to squeeze it into a small enough space. So how small do we have to squeeze the Earth into? So let's get a bit of the audience participation here. So what size do you all think I have to squeeze the Earth into to make it into a black hole? Let's see, I have 3 options here. One is, let's say, the size of about Independence Square, right? So around 100 meters. Or, do I have to squeeze it to a size of a basketball or to the size of a peanut? Let's see. So you can use your emotes or even just raise your hand in your camera. I can see how many of y'all think I have to squeeze Earth to the size of the Independence Square A. You can raise your hands.
I know.
How many of y'all think it's Independence Square?
I tell C. That's a C.
Okay, who says C?
Me. C. I said that's C.
You say C. Okay. How many think it's B?
No. I think B.
B. Okay. I see some B. What about A? What about the largest, Independence Square? How many think it's the size of Independence Square?
It's Independence Square.
Okay, we have some Independence Square. So we have
C.
like all
Yes.
3, some C, but yes, some people who said C are actually correct. So you have to squeeze the Earth into the size of a peanut. So if you squeeze this massive Earth, 6 times 10 to the 24 kilograms, squeeze it to the size of a peanut, it'll become a black hole. So yeah, we have to squeeze it pretty small. Yeah, I think some people got unmuted when they were answering. If yeah, you can mute.
Students, keep your mics muted.
Yeah, thanks for the participation. That was good. So even though black holes are these massive objects, they weigh a lot, they are still pretty small in size. So just keep that in mind. Even though they're pretty big in mass, they're small in size. So I had to squeeze them to a small enough size. All right. So I've told you how we can create black holes, but how does nature create black holes? So nature also has to do this squeezing action into a small enough space, and it turns out that happens in stars. So normally in stars like the sun, what happens is the sun burns elements. So it burns hydrogen to helium to carbon and so on to heavy elements. And as it burns these elements, it releases a lot of light and energy, right? So this energy that comes from burning is what keeps this, sun like puffed up into this massive ball of plasma, basically. So this energy is, released outward. So it creates this outward pressure and it, remains as this ball. But what happens towards the end of a star's life, once it finishes burning all its elements, then it cannot release energy anymore. So what happens is gravity takes over then. At that point, when gravity takes over, the star will start to shrink and contract. And this is really the death of the star. And as it contracts, the inner part of the star is compressed. So this compression is what happens, and it forms this black hole, and the outer layers really hit some wall and expand outwards. So it creates this bright event that throws out a lot of stellar matter. It's called a supernova. So this is really the death of a star. And for stars larger than about 20 solar masses, so 20 times the mass of the sun, this core of the star is large enough so that when it gets compressed, it becomes a black hole. So really, when a large star dies or goes supernova, a black hole is formed. So that's the leading theory for most of the black hole formation in our universe. So these supernovae we have photographed a lot of them with telescopes, and they're extremely some of the most beautiful pictures you see of our universe. For example, Hubble has taken a bunch of these. I show you here. One is Tycho. So this is a supernova, a star that has gone supernova. So this is the outer layers that have exploded. And then here's another supernova here called the supernova nebula, it's called. So this is the remaining, what remains after a star dies. So this is the Cat-Sign Nebula. Here's another one, Cassiopeia. So these pictures look pretty, but just to be truthful, all these colors are not exactly real. They add the color to them just so that we can see the different elements in this supernova. So, for example, if you see it with your naked eye, you won't really see these colors. Even though it looks pretty, it still looks pretty, but they've added this color just to enhance the different elements you can see. So just keep that in mind, despite how pretty these pictures look. And then one is the Crab Nebula here. So this is a star that has exploded, and then in the center there's some sort of object. And then I'll come back to this later. I'll show you the Crab Nebula, so keep that in mind. So this is how black holes are formed in nature. So the black holes that are formed from the supernova that I told you, the stars exploding, the mass of the black hole is around 10 to 50 times the mass of the sun. So 10 to 50 solar masses. But in nature, we have observed black holes that are 10 billion times the mass of the sun. So that's 1 with 9 zeros next to it 10 billion times. So it's still being researched how what are the different ways we can turn 10 to 50 solar mass black holes that are born from these stars up to 10 billion solar masses. And we have a few theories, and I'll go into that a bit in a bit. So these 10 billion solar mass black holes are sometimes they're called supermassive black holes. So they're very massive, supermassive. So this is the creativity of astronomers in naming. So they sort of name it by what it is, a supermassive black hole. So I've told you how nature makes black holes, and now we'll go into how we can actually see black holes. So how in the past astronomers have detected them. So black holes are very hard to detect, right? Because they by themselves don't emit any light. They absorb all the light, and they're very small. Like I said, for example, if you want to make a black hole the size of Earth, it has to be a peanut. The mass of the Earth has to be the size of a peanut. So black holes are pretty small, and they don't emit light on their own. So one way we can observe them is indirectly. So what I mean by when I say indirectly is not exactly look at the black hole, but look at how the material around them behave. So because the gravitational pull of the black hole is so high, if anything comes close enough, it'll move really fast and go if it's orbiting. So example, the sun, orbits the Earth, very nice path. And, by looking at the orbit speed of the Earth and the distance of this orbit, we can determine sort of what the mass and size of the sun is. We can get a good idea. If there's a black hole and if something goes closer, it'll orbit really fast and it'll like orbit in a weird shape. So by looking at something that orbits close to a black hole, we can sort of determine what the mass of the black hole should be. So this was actually done for the center of our galaxy. So the galaxy that we live in, the Milky Way, at its center, it's believed to have a supermassive black hole, so a black hole that's more than 1 million times the mass of the sun. So astronomers, what they did was they tried to zoom into the center of this Milky Way galaxy to try and see how objects around the center move. So that's what I'll show you here. It's a movie of a zoom in. So this is the Milky Way. If you see it, just standing, you can see sort of this haze. Now we'll zoom in more and more towards the center. And as we zoom in, you'll see soon a bunch of stars that are orbiting in a very weird path. So this is really the heart of our Milky Way galaxy. And these are stars that you see here. You see this star here orbiting like really fast. Do you see my mouse, by the way? This is sort of important.
Yes, we can see.
Okay. My pointer, that's good. So you see these stars, so I'll show you a bit more clearer picture. The star is quickly like coming here and then suddenly turns around very fast. So this time lapse is taken over 10 years, so it's pretty long. So here I'll show you its path. It comes and bam, goes like that. So looking at this speed, I'll show you a bit now more latest observations of these different stars orbiting this central object that's here that we can't see. So this is also taken over 10 years, very long time. Right? So by looking at this orbit of these stars, so these are all stars, the velocity and the shape, we can sort of get a good idea of what the object at the center is, how big it is. So it's believed that there's a 4 million solar mass black hole. So this is a supermassive black hole in the center of our galaxy, the Milky Way. And actually, a lot of this research really laid the groundwork to now the idea that every galaxy, the center of every galaxy, has a supermassive black hole, and it plays an important role in galaxy formation. So this is one way of indirectly seeing a black hole. You can't actually see it. It's very small. It's still too small to see. But we can see how things move around it. So there's another way we can indirectly observe black holes. So remember I said black holes on their own do not emit light. However, if you put some matter around a black hole, you actually get very bright signals. So it's kind of weird if you think about it. A black hole is supposed to be an object that really pulls in all the light where anything can escape. But then if you think about it a bit more carefully about how they can be so bright when there's other material around it. One thing you have to keep in mind is that since light below the event horizon can't escape, all the light that comes from a black hole or matter around it has to come from outside the event horizon. And if you think about it, the amount of energy required to actually pull light and prevent it from escaping or any sort of matter has to be large. So the amount of energy around a black hole, that it exerts on matter has to be very large if you want to prevent light from escaping. So imagine if I can just take 10% of that energy somehow around the black hole and then convert it into light or something. That will be a very bright emission because of how much energy this black hole exerts. So this is sort of the idea of what happens when matter surrounds a black hole. This matter gets energized, it gets heated up from this gravitational pull, it gets energized and it emits some light before it goes into the event horizon. So this is the sort of light we observe coming from around the black hole. And if you take a real simple diagram of it, this is what any matter surrounding a black hole would look like. So it will form this sort of what's called an accretion disk. So this is the matter that comes in, it orbits this black hole and eventually will fall in. But before it falls in, it gets heated up, compressed, emits a lot of light. And we can observe this light. So this disk is a disk of superheated plasma. And then even in some conditions, if some conditions are satisfied, for example, if the black hole is spinning fast enough, if this disk is has a sufficient magnetic field, in some cases, right before this material falls, it will actually get shot out in this beam of what's called a jet. So these jets are very powerful. They travel at almost the speed of light. They're basically beams of plasma traveling out. Under the right conditions, you can actually see black holes shooting out jets. So remember, all these don't come from inside the event horizon. Again, that I have to stress that these come from outside. So we actually see these jets in nature. It's pretty cool. So here's one we see in a galaxy called Cygnus A galaxy. You see these long jets propagating outwards, and the distance that we see here is 10 to the 18 kilometers. So one with 18 zeros next to it, right? It's a very long distance that it can travel. And from the energy emitted, again, you get an idea of how big this black hole is. This is 10 billion solar mass black holes. So this is huge. So remember, the black hole, the center of our galaxy, was estimated at around 4 million solar masses. So this is around 1,000 times more heavier or more massive than the black hole in our galaxy. Here's another example from another galaxy where we see these jets. Again, around a 10 billion solar mass black hole is estimated. And this one, we actually have a more zoomed in picture that shows over time how this black hole evolves. So here I have a time lapse of around 6 months taken from telescopes showing this jet. You see this jet material traveling outwards in this time lapse. And the black hole is in the center here. So if I can get this bar to go away, you don't actually see the black hole here. The scale is very large. So the black hole is like, so if you consider this green circle here, the black hole is around 200 times smaller than this green circle. So it's very small, so you can't see it here. So this is what the center of this galaxy looks like. But I'll actually show you later on how people actually can manage to photograph the black hole at the center here, even though it's very small. It's very far away. So, it's very small in the sky. So it's pretty impressive how they've done that. But keep this in mind. This is the M87 galaxy. This is the supermassive black hole somewhere in the center here we can't see. And this is the jet that it emits, and it propagates out here much larger distances. So that's another way of indirectly seeing these black holes, right? By seeing the emission that comes from the matter around it. These jets are very powerful. Like I said, they are about billion to a trillion times more powerful than the sun. So these are big black holes. They have a lot of energy. Then they're spinning, and they emit some of it out in this form of these jets that are very powerful. So now I'll go into how we can actually directly observe black holes. So this time not by seeing things, what's happening around them, but actually seeing the black hole or signals emitted by the black hole itself, not by the material around it. So before I get into the first way of directly observing black holes, I need to introduce a bit what are called gravitational waves. So any mass that moves, or in more accurate terms, that accelerates, you can just think about any mass that moves, emits what's called gravitational waves. So these waves are sort of like light waves, so they propagate at the speed of light. But the gravitational waves, what they do is they warp space-time as they travel. So any mass that moves emits gravitational waves. These waves squeeze and stretch space as they move through. They squeeze and stretch space. They also speed up and slow down time. So they're very weird waves, but they're pretty cool to study as they move through. So this is sort of a picture to help you understand. This is an animation. So this is not, don't take this with some sort of physical accuracy. This is just to help you picture it. So this is, for example, let's say two stars orbiting each other. They do emit gravitational waves. So I show them by these waves here that that propagate through space-time. And as they propagate, like I said, they squeeze and stretch matter, and they speed up and slow down time. So here is an example of what I show you it would look like if it was, very strong. So this is very exaggerated. So this is not the scale at which it will speed and slow down time. This is just for illustration purposes, right? So if gravitational passes through Earth, it'll like squeeze and stretch it like this, like I show you. But again, this effect is extremely tiny. It's not like what you see here. It's extremely tiny because gravitational waves are pretty weak. So it turns out that the more massive an object is, and the more it moves, the stronger the gravitational waves they emit. So black holes are naturally a good candidate for observing gravitational waves because they are massive. They are very compact, right? They're high density, but they're massive, right? They can go up to more than 1 billion times the solar mass. And they can also move very fast, as it turns out. I'll show you a system where they can do that. So in some cases, they can move at close to half the speed of light very fast. So they are a good candidate to observe gravitational waves. But like I said, to observe them, you have to observe this tiny squeezing and stretching in space-time, right? And to do that, people actually built detectors in 2015. This is when it was finished. This is called the Laser Interferometer Gravitational Wave Observatory, or LIGO for short. So this observatory is basically two arms, so two 4-kilometer arms. So you see one here, and then there's one here, two 4-kilometer arms. And in these arms, there are lasers pointing that goes back and forth. There are lasers here. And I show you here a diagram here. So these lasers are these two arms. And as the gravitational wave goes through it, these arms shrink and contract because the gravitational wave stretches and squeezes space as it propagates. And you can actually measure this stretching and squeezing of these arms. And that's how you detect gravitational waves. But this has to be very, very sensitive because like I said, gravitational waves are weak. So the squeezing and stretching is extremely small. The distance of this squeezing and stretching is about 1 billion times smaller than the size of an atom. So it's very small. So, but these detectors that I showed you are capable of detecting that movement of less than 1 billion times smaller than the size of an atom. So extremely sensitive instruments. So I'll show you here in 2015, LIGO actually detected gravitational waves for the first time from two black holes that orbit each other. So two black holes that orbit each other move very fast, and what happens is they get closer and closer until eventually they kind of merge into one black hole. And this emits a lot of gravitational waves. So here I'll show you this movie. So these two black holes are orbiting each other. They emit these gravitational waves you can see in this green region. These gravitational, so this is a big black hole formed in the end. These gravitational waves propagate out at the speed of light. And it took about 1.3 billion years for these gravitational waves to reach Earth. So as they reach Earth, like I said, they squeeze and stretch matter. This is again, this vastly, exaggerated. This is not how much they squeeze and stretch it, right? They squeeze it by like less than 1 billion times the size of an atom. But these gravitational wave detectors here can detect that squeezing and stretching. So it detects this less than 1 billion times movement caused by the gravitational waves. And this is what the signal looks like from this detector. So this is what you see here is the time on the x-axis. So as the gravitational waves pass through, as the gravitational waves pass through, they sort of stretch and squeeze and stretch and squeeze and stretch and squeeze and stretch and squeeze until here is where really the two black holes join together to make a big one. So you get a powerful gravitational wave signal and then nothing. So that's done. The merger is done. So from this data here, from this signal, you can sort of estimate what the mass of the two black holes that were orbiting each other. So it was about 30 solar masses each. So these are 30 solar mass black holes, probably formed from a supernova. And they merge and form one big black hole of more than 50 solar masses. So remember, I told you that black holes formed from these stellar deaths or supernova are expected to be up to 50 solar masses. So these black holes formed are, basically two black holes that are joining together to make a bigger one. So they can form much bigger masses. So hundreds more than even 100. So this is one way that people believe that these big black holes are formed of 10 billion solar masses that we see in the universe. So one way is that we have many small black holes merging together and then they form bigger and bigger ones. Another way that they can form is just by absorbing a lot of matter. So these disks that I showed you around black holes, as they fall in, that mass from that material that falls in goes into the black hole and grows it. So that's another way of growing these black holes. So this is pretty interesting result, very recent. So since 2015, more than 100 black hole mergers have been detected. So the next direct observation I'll show you is what I think is probably the coolest. It is actually photographing a black hole. So think about actually going out and taking a picture of the black hole. And like I said, this is very difficult to do because black holes, for their mass, are very small. They are extremely small for their mass. So you need a very powerful telescope to actually see a black hole, that's far away. So the general rule for telescopes is the larger the telescope, the more smaller the object you can see. So what people decided was, okay, to really see a black hole, let's use a telescope the size of the Earth. So now you must be wondering, wait, there's no telescope the size of the Earth. But what these people did was pretty smart. They used many telescopes around the Earth and sort of took a joint observation so that this acted like one big telescope. So this is called the Event Horizon Telescope Network. These are a bunch of radio telescopes all around the world. So there's some in Greenland, Europe, South America, Antarctica, America. So you have around 9 or 10 of these telescopes that what happens is they take all these observations together and you sort of combine it to try and make it into a telescope that's the size of the Earth. So this is, I explained it to you in 2 minutes, but the amount of work that goes into actually, carefully joining all these observations is a very difficult effort, but was done. So remember, when I showed you jets from black holes, I showed you one M87. This is the time lapse I showed you. This distance that you see in the sky that's shown here is around 1,000 times the size of the black hole. So the black hole is like, 1,000 times smaller than what's shown in this picture. You can't see it. But what happened is astronomers used this Event Horizon Telescope Network to zoom in to the center here and actually photograph the black hole. So I'll show you this zoom in time lapse. So this is what, it would look, oops, I spoiled it a bit. Okay, so now we're zooming into this galaxy from the Earth. This is what you'll see. So they show the constellations. I begin zooming in, zooming in, zooming in. Here, you'll see this is what the M87 galaxy is. So at the center of this galaxy is this black hole. So I keep zooming in. Zoom in. Here you see the jet coming out. This is the jet coming from the black hole that we saw before. The jet still coming out. I zoom in all the way to the center and we come at the black hole. So this is the first photograph of a black hole taken in 2019. Extremely difficult task, but astronomers had done it. So around this, so this is really the shadow of the black hole. You see the black hole is inside here. So no light escapes from below the event horizon. So that's why you see this dark spot. Around it, you see some light. So that comes from this disk that I showed you of this matter that's surrounding it. So really this disk is what's lighting it up around it. And this black hole is 10 billion solar masses. So actually, if you take the distance from here to outside, the entire solar system will fit in this black hole. So it's quite big, but small in astronomical terms for its mass. But the people had managed to photograph it. So these telescopes are extremely powerful, right? They're the size of the Earth. So just to get an idea, they can take a they can take a clear picture of an orange on the moon. So if you put an orange on the moon, this Event Horizon Telescope can take a clear picture of it. That's how powerful they are. So they did a similar sort of thing for the Milky Way. They looked at the center of the Milky Way and they were able to take a photograph of that too. So this photograph is not as clear. Even though the Milky Way is closer, remember the black hole is about 1,000 times smaller. So it's a smaller size. It's a bit more difficult to take a picture, but they somehow did it. And the size here is a bit smaller. Like I said, this would be the sun and this would be Mercury's orbit. So the black hole diameter is less than Mercury's orbit, whereas the black hole I showed you previously, the entire solar system will fit in it. So this is the most recent way of actually directly observing a black hole. So now I'll quickly move on to neutron stars. I have to talk a bit about them too. So they are the smaller cousins of black holes. So neutron stars are also made during supernovae. So when a star dies at the end of a star's life, but they're formed from stars that are not as big. So about less than from about 10 to 25 solar mass stars. So the cores of the stars are not large enough so that when they get compressed, they don't form a black hole. Instead, what happens is, so again, I show you this animation at the end of the star's life. This thing collapses, the core is compressed. The core's mass is not large enough, so it forms a neutron star. So a few facts about neutron stars. So neutron stars are generally what we find is they're between about 1.5 to 2 solar masses. So not like black holes that range from 10 to more than 10 billion solar masses. So this is a very small mass range. So if you anything bigger, this neutron star will collapse into a black hole. It becomes too massive. They have a radius of around 10 kilometers. So we find that these things are pretty big, right? You're fitting the whole mass of the sun into a ball the size of 10 kilometers. These things can spin more than 500 times in 1 second. So they can spin extremely fast for how massive they are. They can have extremely strong magnetic fields. So if you take a fridge magnet, you know what you stick onto the fridge, the neutron star magnetic field is around 10 trillion times more stronger than a fridge magnet. So very strong, spin very fast. So they have this immense amount of energy. And some of this energy gets released and is what we see when we observe them. And they're the second most dense object in the universe, the first being black holes. So all these black holes and neutron stars, they're formed when you compress really matter into a small enough space. For neutron stars, this matter is not massive enough to form a black hole. So it forms the second densest thing, which is called a neutron star. So just to give an idea of how dense they are, a teaspoon, if you take a teaspoon of neutron star material, it'll weigh as much as, let's say a mountain in the Himalayas on Earth. So extremely dense material. What makes them so dense? Well, to understand that, we need to look at what matter in general is made out of. So normal matter, what you find on Earth, wood, metal, whatever, is made out of atoms. So atoms have protons and neutrons grouped together in the center called this nucleus, and then you have some electrons surrounding it. So this is really, many of these atoms arranged together is what forms all the matter that we interact with in our daily lives. So what you'll notice is that since these atoms have to be sort of arranged together, there's a lot of space between them. So they can't really be packed into a small space because these atomic structure prevents it from being compressed. But what happens in a neutron star is this compression really squeezes nucleus together. So these nucleus that found the center of an atom are really squeezed together. And then sometimes you also get these individual particles, electrons, protons, and neutrons, squeezed together to form this sea of electrons, protons, and neutrons. So this is sort of the material that's found in neutron stars, or believed to be found in neutron stars. And this material can be packed into a much smaller space. So they have a much higher density. And this is what really makes a neutron star so dense, because they contain these nuclei and neutrons, mostly neutrons. So they're called neutron stars because they're believed to be made mostly of neutrons, and some electrons and protons also just freely flowing. And it's not 100% known what's in a neutron star. We just know part of it. People are still studying it because these are extreme matter. You can't experiment on Earth. There's nothing you can do to sort of create a neutron star on Earth. So we have to get an idea from what we see in the universe. So it's not completely known 100%. So like I said, neutron stars spin very fast. They have magnetic fields, so they can emit a lot of energy. And we can see some of this energy, actually, if we look at the point telescopes at some neutron stars. So I'll show you one. So remember, I showed you the Crab Nebula earlier, which is what a supernova remnant. So this was a long time ago, a star went supernova, it blew up, it emitted all this stellar material around. And then actually in the center, astronomers found what was left behind was a neutron star. So if I switch, I'll show you now what it looks like when I switch the telescope to X-ray. This is what it looks like in the center. And then we have a time lapse actually of this neutron star emitting these winds. So it's rotating very fast. It is a strong magnetic field. And then this is what powers this winds that you see that's coming out, and even a small jet that's sort of there as well. So this is how we observe neutron stars directly. It's pretty cool that we have an object that's nearby. So the Crab Nebula is sort of nearby, close enough that we can see the center here. So we can also observe gravitational waves from neutron stars. So remember, gravitational waves are emitted by objects that are massive enough, that move fast enough. Turns out black holes and neutron stars are also good candidates. So what happens is when here's an object system where two neutron stars orbit each other, they emit gravitational waves and they crash into each other, but this time they emit a lot of material. Unlike in a black hole merger, there's a lot of neutron star material that comes out in the form of jets. Some neutron star material comes out, from crashing into each other, and it explodes. So this is really neutron star matter that comes out. So unlike a black hole merger, neutron star mergers also emit a lot of light because of all this material that comes out from the neutron star. And it turns out that this neutron star material is very heavy. So like I said, it's made mostly of neutrons. And these are the building blocks of the elements that we see. Before we get to that. So this is what the gravitational signal looked like from the same LIGO observatory, those two arm detectors. So they detected this thing. And it turns out by measuring the light coming from a neutron star merger, what we saw was a lot of the heavy elements that we see in the universe were formed from this neutron star matter that comes out. So a lot of, for example, gold, AG here, gold, platinum, so very precious metals are formed from this neutron star merger, from this neutron star matter that's ejected after neutron star merger. So it's believed that now the lot of the heavy elements that we see on Earth in the solar system are sort of formed from these neutron stars crashing into each other. So I'll just summarize here now what we have seen today. Black holes and neutron stars are the densest objects in the universe, and I think they're the coolest objects in the universe. That's why I study them. They are formed by supernovae. It's the leading theory. So they're formed from stars that explode at the end of their lives. They're some of the brightest sources in the sky. So despite a black hole being a black hole and absorbing all light, it's still some of the brightest sources in the sky. And many of the elements found in the solar system and Earth are believed to come from both supernovae, so exploding stars, and neutron stars mergers. So we are we are probably all made from, you know, star matter and neutron star matter that was made billions and billions of years ago. So before leaving, if you're really interested in this material and you want to really learn more or see more about this, I can recommend a few educational resources. So these are free channels on YouTube. Actually, I watched a lot of these also a while ago, and these channels, PBS Spacetime, for example, does a very good job of explaining all different sort of objects found in the universe. So these are just science and space channels in general, not just restricted to black holes and neutron stars, but space and science in general. Nova PBS, so these are very good channels, Kurzgesagt and Veritasium. So they'll probably do a better job of explaining a lot of the things that I did show here. And they also have very cool movies and animations to help you understand everything we speak about. So I'll end it here and take your questions. Thank you.
Thank you very much. I do believe that all the students, they enjoyed it. So I think we have Sudhita who wants to go first. So Sudhita, you may ask your first question.
Sir, actually, what will happen if a black hole collapses?
So a black hole is already collapsed. So it's matter that's collapsed that has formed a black hole. So a black hole can't collapse any further. It's really the result of not being able to collapse any further is what forms this black hole. So normal matter is what collapses and forms a black hole. I'm not sure if that answered it, but yeah. A black hole can't collapse any further.
Right, thank you for that, Dr. Adithan. So next we have Vinal. Vinal, you may ask your question.
Okay. Doctor. Hello, doctor.
Hi. Yeah, I can hear you. Hi.
What if a black hole and a supernova? There's a supernova behind the black hole and in front of the black hole, and there's another black hole in the left side.
So you're saying there's a black hole here, there's a black hole here, and a supernova happens in the middle?
Yeah.
Well, depending on the size of the star, it depends. But so when the supernova happens, you have some of this star material that's blown out. So some of that will be absorbed by a black hole on the sides. So they'll form, some will get absorbed, some will form a disk, a very small disk, it won't be much. So yeah, the black hole might absorb some matter, it might emit some light, the supernova will emit some light, and then something will be left in the middle depending on the size of the star. But actually, this is pretty interesting. So these two black hole orbiting each other animation that I showed you, where these gravitational waves emitted, one way of forming this is by, you have initially two stars that were formed close to each other that orbit each other. So we have observed in nature, most of the stars actually exist in what's called these binary systems. Binary means two. So they exist in two systems, two stars orbiting each other. Most of the stars have like this companion. And then one star at the end of its life will explode, maybe form a black hole. The other one, so then you have a black hole and a star orbiting each other. Then at some point, the other star will die and explode, form a black hole. And then you have two black holes orbiting each other. And this is what really, one way of forming these two black hole systems that we see in gravitational waves.
Okay, thank you.
Yeah.
Thank you for that, Dr. Adithan. Next, we have Adithan.
What will happen if two neutron stars collide? Would they create a black hole? And what happens if they do? What happens to them when the collision happens?
So this is a very good question, and it's a good question because researchers are still trying to understand exactly. So when the two neutron stars merge, what happens is you have a slightly bigger object that forms in the center, and all this neutron star matter some of it gets thrown out. So it's not 100% understood. In some cases, what we believe happens is, depending on the two neutron stars, sometimes the central object immediately forms a black hole because it's very heavy. In some cases, they believe that it will be a very massive neutron star for a short amount of time, and after about less than a second, it'll become too heavy and collapse into a black hole. But these are still active, ongoing research problems because we don't completely understand what a neutron star is completely made of. We have an idea of some of it, but not complete knowledge of what a neutron star is made of. So yeah, it's not 100% understood, but it's most likely a black hole or a very massive neutron star and black hole.
Thank you for that, Dr. Adithan. Next, we have Ayusha.
Excuse me, Dr. Adit. What would happen? What is the most biggest black hole that is found to this day?
I don't have it off the top of my head, but I think it's around 30 or 40 billion solar masses that is detected. Yeah, so it's 60 billion solar masses is
66 billion.
66 billion, yeah.
Thank you. So we have Imalka, I think. I think he's asked. Yes, Imalka, you may ask your question.
Can you squeeze the sun and smaller than 2 kilometers, like smaller than 3 kilometers, like 1 kilometer, or maybe to the size of atoms?
So once we form a black hole, so when the sun is squeezed to 3 kilometers, we really don't know what happens inside that. So we can't control what happens inside that 3 kilometers. So inside it, there can be, the sun might be squeezed into something the size of an atom, but we don't know. It's really disconnected from the outside universe because of this event horizon. So we can't do anything about that. We can't squeeze the sun smaller than 3 kilometers, or nature can't even. So
Thank you, sir.
Yeah.
All right. So thank you. Ansaru, do you have a question?
Okay, well, actually, I don't know how a black hole make.
So a black hole in nature is formed from this supernova. So if you have a normal sun, let's a star that's larger than about 20 to 30 solar masses, so something that's 30 times more massive than our sun. What happens is, at the end of a star's life, when it has finished burning all its elements, it can't release much energy to really keep the star's shape. So in the star's life, you're constantly fighting gravity, right? The star is constantly fighting the gravitational collapse by emitting this energy that comes from burning elements. So this energy releases some outward pressure that keeps the star its shape and prevents it from gravitationally collapsing. But what happens when the star is finished burning all its elements, it really can't have this outward pressure. So gravity takes over and it starts to get squeezed down. And the core of the star is believed to be squeezed to a very small space. So this squeezing is what forms this black hole. And then the outer layers of the star, as it falls in, it gets squeezed, and then at some point it forms this very dense object, this black hole, and it's basically like these outer layers hit a wall at some point and then explode out. So these outer layers will explode out and form this beautiful supernova nebula that you see in telescope pictures, and at the center you have the remnant, what has been squeezed, it has formed a black hole.
Okay, I got it now. Thanks for teaching.
Yeah.
All right. Thank you for that. So is there anyone else who wants to ask a question? You can keep it short. That would be great. Arudit, do you want to go? Okay, Arudit.
I'm interested in it. How can kids join the researchers?
Sorry?
I am really interested in them. How can kids join the researchers?
So this is good. So if you're interested, keep learning. Like I said, there are these nice resources on free channels on YouTube where you can learn more. You have to, finish school, make sure you do well in school. So that really starts the foundation. And then once you finish school, you have your O-level, A-levels, presumably you can pick your science subjects. And then you have to go to university. So about 4 years, you have to study your what's called the university undergraduate. So in that you take more physics courses, maths courses, you learn a bit more advanced. So you can then pick what field you want to sort of go into in those 4 years after school when you go to university. So you can choose astrophysics, you can choose physics, so it's a lot of studying. And then after you do those 4 years, then you have to do what's called your PhD. So that takes about 5 to maybe 7 years after that. So, about 10 to 12 years after you finish school, you have to keep studying, you research, you pick your field you want to go into. It might be physics, astrophysics, or maybe some other science subject that you become interested in later on. And then after you finish your PhD, then you can get a job in research. So do what all these cool things that I showed you that made us able to see these black holes and neutron stars were done by these sort of people who had, studied about 10, 12 years after school, did research for about 5, 10 years afterwards, and they just continue doing it to this day. So you just have to start, I guess, now by just doing well in school, understanding, if you're interested in these topics, a lot of free resources like I showed you. You can look it up in your free time, just watch it if you're interested in. And yeah, that's how it goes.
Okay, that was great. Is there anyone else who wants to ask a question? Anyone else? I can see. Okay, Sudhita.
Time, Bina.
All right, Bina.
The massive supernovas if 3 supernovas collapse with a neutron star, what will happen to the neutron star?
What do you mean by 3 supernovas?
3 supernovas collapse into a neutron star.
Yeah, so there are 3. So each supernova means there's a separate star. So do you mean like you have 3 stars next to each other?
No, there's one supernova. There's 3 supernovas and one giant star. Then they collapse. What will happen?
I am not understanding the question. So can you maybe explain what you have in mind when you say 3 supernovas?
I mean, there are 3 supernovas, and there's a big a star in middle of the supernovas. Then they collapse into it. What will happen? It will blast. Then what will happen to the star?
So how do you picture the stars arranged before? So do you have 3 stars next to each other that blow up? Is that what you're picturing? So you have 3 stars next to each other, and in the center you have another massive star?
Yeah, I'm saying that.
Okay, so if the 3 stars around it like go supernova, then I think what will happen is, so the explosion from these 3 stars and the wind will sort of can what's called strip this middle star from its outer layers. So what can happen is this middle star can lose some of its mass from this explosion, and what happens after depends. If they form a neutron star, then some of the neutron star winds that I showed you in the animation can sort of still affect this big star. But other than that, yeah, I'm not sure. Something like this, I don't think has been really seen in nature, so it's sort of difficult to picture exactly what will happen.
Thank you.
Right. So thank you for that, Dr. Adithan, and thank you for answering all the questions that our kids were having. So it was really enlightening, and I believe all the students here present have learned something new regarding black holes and neutron stars. So thank you very much for accepting our invitation, Dr. Adithan. It was really great, and it was a really good opportunity for our institute as well as for our students. And also, unfortunately, Miss Wendy could not join us today, but she is watching the live from her end. So thank you very much for that, Dr. Adithan. I hope you will join us again in our upcoming sessions. It would be really great if you could.
Yeah, thanks everyone. Thanks for organizing it, and see you all.
All right, Doc. Have a nice day.
Bye. Have a good night.